Welcome to module number 5 in our series on artificial intelligence. This one discusses supervised machine learning as applied to the Perceptron neural network. And this module provides a really nice jumping off point for later modules in which we will discuss machine learning as applied to more complex neural network structures, such as those that employ deep learning or multiple hidden layers. Let's quickly review the topics discussed in recent modules. Modules 1 and 2 introduce the concepts of artificial intelligence, machine learning, and neural networks on a pretty fundamental level. Modules 3 and 4 discussed parametric modeling, linear regression, as well as logistic regression. We also compared and contrasted those topics with one another. Let's move on to a quick overview of the topic to be discussed in this module. And the first question that I want to address, it's one that we've addressed before, is what is machine learning? So there is a little bit of repetition here. Machine learning is a field of study within AI, tasked with the development of generally iterative, not always, but generally iterative, statistical methods and algorithms that accept training data, learn relevant patterns and relationships from that training data, as well as generalize and apply those learned relationships to new cases or new data sets. We may visualize machine learning like repeatedly shooting a free throw, something I think we've all done at least once in our life, right? We make small adjustments to the way that we shoot until consistency is achieved. We shoot the ball, it goes too far. What does that mean? We have to reduce the strength with which the ball was thrown, and that strength, we can equate that to a variable. And what we can see is that machine learning employs a very similar process. It tries out inputs, compares the ideal and actual results to one another, and then adjusts the variables in order to improve performance. Let's say we shoot the ball too far to the left. Again, that's another variable we can adjust. We can aim our body more to the right. And what happens if we make the shot, right? If we succeed, then we want to do nothing. We don't want to adjust any variables. Before we can apply machine learning, there are several questions that must be considered. For example, do we have labeled training data that facilitates supervised learning if we want to use supervised learning? Or do we prefer to use an unsupervised approach, such as that associated with clustering? What model should we employ? A logistic regression model, a neural network? There's many different options there. How can we maximize the effectiveness of the machine learning model and optimizer by properly initializing variables like the synapse weights, by increasing or decreasing the rate at which learning occurs, and or increasing or decreasing the connections between nodes? And this again obviously would only apply to a neural network. Specifically, this module focuses on implementation of a supervised machine learning algorithm that employs a basic error correction rule in conjunction with a single layer perceptron neural network for binary classification. Now, it may seem like I just threw a whole bunch of terms at you. However, each one of these terms is one that we discussed in a previous module. Now, in this module, we employ an example to demonstrate how this concept may be applied to a practical real-world problem. We're actually going to use the same example from the previous module, the one with the small animal that's trying to identify what food it can eat. We will employ both by hand and software-based calculations, and we do provide QR codes that act as links to all the scripts so you can download and play around with those at home. I'm also going to provide a homework exercise for you to attempt. That's at the very end of the module, and as always, our objective is to communicate practical useful machine learning skills. And quick note, if you are looking at some of the MATLAB scripts and you don't have access to MATLAB, I do provide a link to something called Octave Online, which is a really great online free MATLAB alternative that you can use to run these same scripts. So let's return to our main discussion, and the first topic that we're going to address is machine learning characteristics. So what are the primary characteristics of a machine learning implementation? And we use that word implementation to sort of encompass everything associated with the machine learning algorithm, the model and the problem, everything. So the three characteristics that I'm going to define, the first is the components, right? They describe the data and the mathematical structures required, or that must be defined for any machine learning implementation. And one example would be the model used. A second characteristic is the learning approach or paradigm employed, and this describes how patterns of interest are observed and mapped to the parameters of an assumed model. Now, within the learning approach, there's a sub-characteristic that I'm going to define. That's the learning rule or the learning strategy. And this describes specifically how error is quantified as well as how parameters are tuned to reduce that error. So this sort of gives us the specifics of how we're going to update values within the training algorithm. The third characteristic is the application, and that describes the practical objective of any machine learning implementation. And one example could be classification, which is an application that we worked with within the logistic regression module. So now discussing these characteristics in greater detail, the first characteristic, right, was a description of the components involved in a machine learning implementation. And I've defined several components here. This is not all inclusive. Depending on the implementation or the type of machine learning algorithm you're trying to implement, these components may change slightly. But for the example that we're looking at here, supervised learning for binary classification using a perceptron, this is a pretty good guide. So the first component would be the training data set, and this contains the input-output pairs that we want to mimic. Within that, or let's say a subset of that, we also have the validation and test data sets. And often, that can be extracted from the training data set. The most important thing to realize is that we do not want to test our machine learning algorithm using the same data that was employed to train it, right? That's going to lead to a significant amount of bias in the way that our machine learning implementation works. We always want to have a separate validation and testing, and that could be one, so separate validation and testing data set to employ. Now, the second component is the model. And this defines the mathematical input-output mapping for a system. We've already looked at several different models. The logistic regression used its own logistic model. The neural network itself is a type of model. Now, associated with the model is the parameter set, which we refer to as theta, and that tunes the model behavior. And we saw this, it was very well demonstrated in the linear regression and the logistic regression models, where we had, for the linear model, it was y equals mx plus b, and what we saw is there was two parameters, m and b, which we called theta 0 and theta 1, and the whole point of the linear regression algorithm was to come up with optimal values for those parameters. A third component is the loss function, and this quantifies the accuracy or the optimality of a model and its associated parameters. It quantifies error, right, generally in terms of the difference between an ideal output and an estimated value that our model generates. A fourth component is the optimizer or the optimization method, and that calculates the optimal parameters, which we call theta sub OPT, such that loss is minimized. For linear regression, going back to some of the recent modules, right, for a linear regression, we had a closed form solution which served this purpose, right? We could use this equation right here and come up with our optimal parameters. For logistic regression, we were dependent on a minimization. I don't have the whole equation here, but you can see the beginning of it. Now, one thing to note here is that nonlinear system optimization is difficult. So the task of optimizing and solving for the optimal model parameters is not always going to be an easy one, and it's going to be one that's often going to require extended discussion. A second characteristic is the learning approach or paradigm, and I present three here as an example, although others exist, other separate paradigms as well as variations on these. One is unsupervised learning, right? The objective is to identify hidden patterns within unlabeled data. The training data for an unsupervised learning algorithm does not require labeling nor ideal input-output pairs. And example applications, right, one would be the k-means clustering algorithm, or really any clustering algorithm. The second learning approach or paradigm that we look at is supervised learning. And the objective of supervised learning is to mimic complex patterns within labeled data. The training data does require ideal input-output pairs with appropriate labels. So the training data needs to tell us for each sample what the ideal output should be. We call that the label. Example applications include problems related to linear regression as well as neural network training, and that kind of brings us back to the topic we discuss in this module, right? We are using supervised learning here in this module. The third type that I wanted to discuss is reinforcement learning, and the objectives of reinforcement learning are to mimic complex behavior within a dynamic environment, and often this is done in real time. Now, training data for reinforcement learning, it consists of indirect rewards and penalties yielded via trial and error. It's kind of like supervised learning, except the observations may be generated on the fly via hardware or software simulation, perhaps in the loop. But it's unlike supervised learning in that ideal outputs are not acquired directly, right? We don't get an ideal output. What we do is receive indirect rewards or penalties that help guide the machine learning algorithm in the right direction and instruct it how to update various parameters. Example applications include games like chess, or using machine learning to play or optimize games like chess. And then another example would be the Q-learning algorithm for self-driving vehicles. Now, like I said a second ago, there are other paradigms or other variations on these paradigms, which we'll discuss at a later time. Now here's a quick comparison of unsupervised versus supervised learning. I got this figure from a website called Database Town, so thanks for that. I don't think we need to go through this in too much detail, but the main difference between the left side and the right side here, the unsupervised and the supervised learning, is that on the left we have unlabeled data. On the right, for supervised learning, we have labeled data. And what that means is we know this is a tomato, we know this is a carrot, and we know this is a pepper, right? The training data tells us so. Now, the unsupervised learning algorithm, what it does is takes these inputs and places them into various bins or categories. This is very similar to what certain types of supervised learning algorithms can do if they are focused on classification. So here we see we've taken the inputs and assigned them to the bin of carrot, bell pepper, and tomato. So what's the difference, right? They're both kind of doing the same thing. On the left-hand side with the unsupervised learning, we don't know what the names of these categories are, right? It separated the input data into clusters, but we didn't define what those groups were. Whereas on the right-hand side, for the supervised learning, we essentially defined these groups over here in accordance with the labels that were provided as part of the training data. So unsupervised learning is generally associated with clustering type problems, whereas supervised learning can tackle a wider variety of problems where we're trying to mimic some ideal input-output relationship. So underneath characteristic 2, the machine learning approaches or paradigms, we also define sort of a sub-characteristic, which I'm going to call 2b, and that describes the machine learning rule or strategy used. In this slide, I'm going to present 2 different strategies. Now, there are many others that exist, separate strategies as well as variations on these, but 2 is a good starting point. Now, in this module, we use the error correction or Perceptron learning rule. And the primary application is binary classification, right? Taking inputs and placing them into one of 2 categories. We can quickly summarize the method. The first thing that we need to do is quantify the error or the loss, right? We need to use a loss function. And generally, we just quantify that as the difference between the ideal and the estimated solution. So the ideal solution should be provided by the training data. This is the label that we've talked about before. And the estimated solution should be calculated, generated by the model using the appropriate parameters. And then this expression here allows us to update the parameters from iteration to iteration. So we start off with an initial condition for iteration 0. We then quantify the difference between the ideal and the estimated solutions for that iteration using a training data sample. We multiply that by the inputs as well as alpha. This represents the machine learning rate. We'll discuss that more later. And then all those values together, the product and the sum, generate the parameter array for the next iteration. So iteration it plus 1. Now, in later slides and lessons, we're going to clarify this notation and the meaning of both of the update expressions, this one and the one to the right. So we'll just consider this to be an intro. Now, another very popular machine learning rule or strategy is called gradient descent. And the application, really, it applies to almost everything. It's a very broad approach. The method we can quantify or we can summarize in about 3 steps. Like the error correction, we need to define error or a loss function. Now, I'm not going to provide specifics here because we can use various loss functions for gradient descent. We then calculate the gradient of the loss function with respect to the parameters, okay, or calculate the derivative or partial derivative with respect to those parameters. And then we use an update expression, which works similarly to the one on the left. We start off with an initial condition of our parameters. We add to that the negative of the gradient. And why is that? Because the gradient positive would tell us how to best increase the value of the loss function. We want to decrease it, so we take the negative value. And we add those 2 together, and that gives us our parameter values for the next iteration. Now, I forgot to put an alpha value here, but obviously, we could employ a learning rate there as well in order to control the machine learning progress. So the third characteristic would be the application type, and I've created a table to help summarize and compare and contrast these. So we're going to talk about 3 different types. There are other applications as well as variations on these. So the first is numerical regression. The objective of numerical regression is to extrapolate observed input-output relationships. And an example would be, right, let's say we observe historical gold prices and then try to extrapolate those into the future. Now, for a linear regression, which is one that we talked about previously, we are limited by the use of a linear model, but there are other types of similar numerical regressions with more advanced model types that can provide a more accurate answer. Now, numerical regression generally employs supervised learning, which means that our data, our training data, does require labels, and the output is, again, generally going to be a continuous numerical value. The second application is classification, and that's what we're actually going to be dealing with in this module. We also dealt with classification in the previous module when we discussed logistic regression. And I know it's a little bit confusing here that logistic regression falls under the category of classification. That's why I put this numerical here to try to differentiate logistic regression from other numerical regressions. So classification, the objective is to assign inputs to user-defined categories based on observations. And one example would be, let's say we have an algorithm that observes users' email habits, what emails they're throwing into the trash or the spam folder, and then uses that information to, in the future, assign emails to either spam or not spam. Now again, this would be a supervised machine learning algorithm, so that's the learning paradigm that we would use, and for any supervised algorithm, we do require training data with labels. And the output would be the assignment to a user-defined category. So the third application type is clustering. The objective of clustering is to discover hidden groupings within unlabeled data. Now we can compare and contrast clustering with classification because both take inputs and assign them into groups. The difference is that for classification, we're telling the algorithm through the training data labels exactly what those groups are. If we go back to the picture from 2 or 3 slides back where we were organizing the vegetables, right? We had to tell it, right? An item is a carrot. It's a tomato, it's a pepper. We define those 3 label types, and so at the end, we end up with our data, with our inputs split up into 3 bins. With the clustering, we don't have that level of control. The clustering is going to look for these hidden relationships and split up the inputs accordingly. Now, an example of a clustering approach or a clustering application would be to look at a customer database and segment those customers based on behaviors and look for these hidden relationships. Now, clustering does employ an unsupervised learning paradigm and does not require labels for its training data. The output is generally going to be assignment to some naturally emerging cluster. Similar to the type of input that we had for classification. Both of these result in an assignment, but here we have user-defined categories, and here we have naturally emerging clusters. So next, let's talk about the supervised machine learning process. And I'm going to try to break this down into about 7 or 8 steps. Step 1 is to understand the problem and the objective. Now, exactly how we do this, it will vary by application, but we do want to ask ourselves certain questions. What observed behavior do we want to mimic? What predictions do we want to generate? The second step would be to define the machine learning characteristics to meet the objectives to solve the problem defined above. And so let's take a look at some of those characteristics. Now, these are the characteristics we're actually going to use throughout this module and in our example. So the components, the first characteristic, right? One component is the loss function. We're going to be using a loss function, which merely calculates the difference between the ideal and the estimated output. And since we only have a single output, there's only one that we have to worry about. The model is a single layer perceptron neural network. We're going to show a diagram for that in a second. It generates a single yes/no result. And the learning rule or strategy will be the basic error correction, aka perceptron learning rule. So as such, this requires training data composed of labeled ideal input-output pairs. The third characteristic is the application or the application type, which in this case will be classification. We're trying to classify inputs into various categories, or more accurately, we're going to be working with linear classification. It's linear because our perceptron has a single layer structure, and we'll come back to what that means a little bit later on. So let's move on to step number 3. Which is to collect appropriate training data with labels if needed. If we're working with supervised learning, then we will need those labels. I've also defined 2 sub-steps within 3. So 3A, we may need to pre-process the data. That could include normalization, filtering, data correction, removing erroneous data points. Step 3B may be to extract certain features or aggregate data points to reduce the amount of information passed to the model. And one really good example of that would be employing a convolutional layer to extract features from an image. Step 4 is to fine-tune the machine learning characteristics or implementation to address the desired objectives, the problem at hand, to address available training data, as well as any practical constraints that we may encounter. And so here are some questions we may need to ask ourselves. Does the model require simplification, right? Do we need to reduce the number of parameters or synapse connections if we're talking about a neural network? How will our model parameters be initialized, right? If we have a nonlinear model and we have to employ some sort of iterative optimization process, then generally we'll need to initialize those parameters, and the quality of the initialization can have a strong effect on the quality of the result or whether we get a result at all. How is convergence defined? And that's a topic we're going to discuss later. Also, what's the desired learning rate? Do we want the machine learning algorithm to focus on moving very quickly, but that could lead to instabilities, or taking it slow and steady? Now, step number 5, and this is really more of a practical concern, is to develop the necessary software or simulation to conduct the machine learning, and actually to do the work that's described in step number 6. So step number 6 is to train the model to yield optimal model parameters, which in the case of a neural network would be those synapse weights, from training data. And I've broken this down into 4 sub-steps. So the first step, 6a, is to evaluate the model to generate an estimated output y sub est. We then want to update the synapse weights, assuming that this is a neural network model. You can substitute parameters if it's not a neural network. Check for convergence. Again, we'll discuss that more later, but convergence essentially is a characteristic that tells us that our training is done. And if we reach convergence, we skip down to step number 7. However, if we haven't reached convergence, then we need to loop back around and return to 6a and start a new iteration, choose a new training data point to examine, and try to update our synapse weights again to maximize accuracy and minimize loss. Now, I know that this description is not 100% clear. When we employ the example, when we start to discuss the example, I think these 4 steps here will become a lot clearer. The example is the best way to demonstrate this. Now, step 7 is to verify and test the model. After training is complete, we want to determine whether the result is ready for widespread deployment, and so we would use verification and test data for that purpose. Right? We want to answer the question, does the trained model infer optimal results for validation and or test data sets? So next, let's talk about convergence and fitting. Convergence is defined by a threshold value representing the maximum error or delta change in something like synapse weights, below which a model's parameters are assumed or deemed to be reasonably accurate, good enough, representing the point at which the model training stabilizes. The optimization algorithm has sufficiently minimized error, as may be defined here, and overall, further training will not yield significantly more optimal parameters. So the convergence criterion, we could also call that the stopping criterion, is a way that we determine whether the iterative training algorithm has progressed far enough, and that further training is not really worth the trouble. These threshold values must be properly defined. If we have too small of a convergence threshold, if that threshold is too tight, we may end up with overfitting. And what that means is that our machine learning algorithm trains beyond what is optimal, and resulting in a hyper-focus on the specific training data set that it's working with. And that's not a good thing, because it means it won't perform well for other data sets that it may see in the real world. Now, if we have too large of a threshold, or if the constraint is too relaxed, then we may end up with underfitting, and that would be the case where the machine learning is really incomplete. It hasn't finished its job. So these 2 figures help to visualize, to demonstrate the idea of convergence. So for both of these, on the x-axis, we have the iteration number. So you can see this beginning over here with initialization and then progressing to the right towards convergence. On the y-axis here, we have the parameter values for a model, or that could also be the synapse weights. Over here, we have the output, which I'm calling y. Now, for the left-hand side, so there's 2 different ways that we can look at convergence, and generally we use these 2 in conjunction with one another. So if we rely on the parameter values, we can declare convergence when the effect of machine learning updates, aka the slope here, drops below a threshold. What that means is that once the updates to the parameter values kind of even out, and we don't see much change from one iteration to the next, that's an indicator that perhaps the training may have gotten as good as it's going to get. So convergence would be defined as the maximum slope within a given window, right? Because we must look at these values within a window. We don't want to rely on a single sample. Anything can happen for a single sample. But once the maximum slope within a given window drops below a certain threshold, that may be a clue that convergence has been reached, or that training is at least complete. Now, we can also define this in terms of the output, where for this we would be comparing the estimated output and the ideal output. And what we see is that as training continues, we expect for the 2 of these to move closer together, and once the difference between them, right, once the maximum error over a given window, again, we have to rely on a window, we don't want to look at a single value. Once that drops below a threshold, we can potentially say that we've converged and we've reached the end of the training algorithm. Right, for error, right, by luck, we could end up with an error equals 0 for a single data point. So that's why it's so important to make sure we're looking at a window and not a single sample. So in summary, there's 2 main ways that we can define convergence. One is in terms of the output. What we can say is that when the difference between the estimated and the ideal value drops below a certain threshold for an extended number of iterations, that tells us that training is done. The other is to look at the effect of each iteration on the parameters themselves, and once that effect kind of levels out, we can say perhaps this training has progressed far enough. So I wanted to discuss underfitting and overfitting in a little bit more detail. So take a look at this figure right here. Again, thanks to Geeks for Geeks for providing this. Please use the QR code to check out this source. So what we see is a two-dimensional example. We have two dimensions of inputs, x1 and x2. And then we have two distinct categories of outputs, right? We have X's and we have O's. And so we could assume that we're using machine learning to try to categorize these inputs by X or O into one of these two categories. Now on the left-hand side, we see an underfit solution where we have a line going through the middle. I'm assuming that above it is intended to be the O region and below it is intended to be the X region. But you can see that there's a lot of O's that fall into the X region and a good number of X's that fall into the O region. So we could describe this as being underfit, and it generates a result with relatively low accuracy where, again, we have, let's see, 1, 2, 3, 4, 5, 6, at least 7 or 8 erroneously classified inputs. Now on the far right, we see an overfit result, overfitting. And this is the case where we have trained this so much, it does a very good job, right, of separating the X's from the O's. In fact, for this specific data set, it does it perfectly. But this result will fail when applied to a non-training data set. It's so specific to this training data set that it's, one way of saying it is it's gone overboard. Now, the ideal result that we're looking for is one that appropriately fits, right? One that maximizes performance when applied to the training data as well as the non-training data. So we can see here that this linear model perhaps is too simple for this data and yields an underfit result. Whatever is going on over here is extremely complex and highly unlikely to work well for non-training data, but this curve here does a nice job. Now remember, or note that an appropriately fit model doesn't necessarily mean it works with 100% accuracy. We still do have some erroneous classifications here, but it works good enough. It balances the importance of training accuracy with the importance of working or being accurate for non-training validation and test datasets. Next, let's talk about our machine learning model as well as the learning rule that we're going to be employing. So here is a figure of the single layer perceptron neural network that we're going to be using in this module. We've shown this figure before, however, I've made a couple changes that I want to clarify. Okay, so let's go through it piece by piece. First, we have 3 inputs, x1, x2, and x3, all of them being superscripts. If you remember the example from the logistic regression module, right, that could represent inputs such as, is the object red, is it small, and is motion detected. Each one of those inputs is multiplied by its respective synapse weight. Now the way that we label these synapse weights, right, we have W, the subscript tells us what module it's coming from, right? Because you can think of the synapse as spanning the distance between 2 nodes. So this is coming from node number 1 and going to node number M, right? Because the main node that we're working with is referred to as node M. So hence it makes sense that this is W subscript 1 superscript M, W subscript 2 superscript M, W subscript 3 superscript M. Okay, so we multiply all 3 of those inputs by their respective synapse weights. And those are all supplied to a summer that adds those all together. Now previously, we had a separate value that we called the bias offset, and we called that B sub 0. What I did was incorporate that into the synapse weights. Now generally, that was actually subtracted from the rest. So what I did was, so I have this value W sub 0 superscript M, that represents the bias offset, but it needs a value to be multiplied by, right? It needs an input. So we declare this dummy input, which I call X superscript 0, and that's always equal to -1, and so essentially that leads us to the equivalent negative bias offset. So we have, in this case, 3 real synapse weights and 1 sort of pseudo-real fake synapse weight, which represents the bias. So we sum all of these together, we supply that to our activation function, and we end up with our result. And so here's just the mathematical representation of the perceptron. Right, we apply the activation function to the weighted sum of the synapse weights and their inputs. Note that now k starts at 0 instead of 1 because we have to consider the 0th input. And this piece here goes away, right? This is where our bias offset used to be. And we end up with this piecewise representation, right? If the weighted sum is greater than 0, we get a value of 1. If the weighted sum is less than 0, we get a value of 0. This slide goes over the learning rule or the update expression we're going to use to update our synapse weights as part of machine learning. So I'm going to start from the right and then move to the left. This figure up here is the same, so I don't need to discuss it again. So we start over here with the synapse weight between node K and node M for an iteration it. It is just a variable. Now, if it equals 0, then this would be the initial condition right here. We would supply the initial condition to get the ball rolling. Over on the left-hand side, we have the updated value, the same synapse weight between nodes k and m, but for the next iteration, it plus 1. Now, the difference between the previous and the future value of the synapse weight is the product of these three elements. The first is simply a scalar coefficient, which we call the learning rate. Right, a larger value, a larger learning rate means there'll be more change from one iteration to the next, and a smaller value means there'll be less change from one iteration to the next, right? It scales that delta value. The next component is the loss function, or the error, right? This is the calculated or predicted error or loss. It's simply the difference between the ideal output and the estimated output for a given iteration, or the current iteration we're dealing with. And then we multiply that by the input. Okay, x superscript it superscript k, what does that mean, right? It is the input value for iteration it, but looking at element k. Now, note that the variable it represents the iteration and the training data sample. If you remember previously, we had referred to inputs in this way. Let's say we have an input for a training sample, which I'll call t, and we have an element e, right? So this told us what training sample we were working with and what element of that training sample, right? That's for the logistic regression module. In this module, we're doing things a little bit differently. We're defining in terms of an iteration as well as an element. So this has the exact same role. It tells us which element we're looking at, right? And these elements dictate whether we're observing, is it red, is it small, is it moving, again, relating it back to the example. But how do we replace this training sample with it? Now, the way that it works is for each iteration of the training algorithm, right, we're going to need to choose a sample to use. And so all we're doing here in this notation is assuming that it represents whatever training sample is associated with that iteration. Now, there's probably a more formal way of writing that, but I figured this was good enough for the purposes of this module. So whenever you see x superscript it, you can just replace that in your head with the data sample, with the training sample that corresponds to the current iteration. Now, the other question I want to answer is, why do we have this x value right here? Why multiply by x? And there's a very clear reason for that. We only want to update synapses and synapse weights when they affect the output, right? So if this value right here is a 0, then what that means is that this synapse weight doesn't have any effect on the answer, and therefore we don't want to update it. So now let's take a look at an example. I think it'll clear up a lot of the questions that you may have. You've seen this before. We used it in a previous module. We're going to consider this animal's instinct to collect small red berries and avoid predators. It's conditioned to approach an object under the following three conditions, right? The object is small, it doesn't detect any movement. The object is red, it doesn't detect any movement. The object is small and red, and it doesn't care if there's any movement around. Now, there's three inputs, or I should say three observations that we make, or the animal makes. Is the object small? Yes or no. Is the object red? Yes or no. Is the object moving? Yes or no. Now, there's also the fourth input, which is always a -1. Right, this is not an actual observation. It's just the coefficient of the synapse weight, right? That's associated with the bias offset. So that would be multiplied by. Now, this example, this is a little bit repetition here, indexes inputs differently than the previous. We just talked about this. If iteration it is associated with training sample k, so we're using training sample k for iteration it, then x superscript k0, or you could put any number in here, is equal to x superscript it 0, or you could put any number in here. So the equivalency is between these two, and we'll see in the example, I'm clearly going to tell you which training sample we're using for each iteration. So parentheses it maps to bracket k. All right, so the output, right, as we saw before, the animal's brain must generate a single output should we approach the object, yes or no. And our machine learning objective is to employ this supervised learning rule, the single layer perceptron, to calculate or estimate the optimal synapse weights and biases, but now actually we include the bias inside the synapse weight, such that the neural network or the perceptron model accurately represents the behavior shown below. And we've seen this table before, so I don't think we need to take a look at it again. Is it small? Is it red? Is there movement? Should it approach it? Yes or no? Now, we're going to return to the same steps for performing this type of machine learning work that we defined previously. The first step is to make sure we understand the problem and the objective. Done. I think we have a pretty good understanding of the problem and the objective. We just stated those. Step number 2 is to define the machine learning characteristics. That's done. We did that about 10 slides back. If you remember, we talked about what error correction rule we're going to be using, talked about how we're using the single layer perceptron, etc. Step number 3 is to collect the appropriate training data. This is done. It's all included in that table from the previous slide. Step number 4 is to fine-tune the machine learning characteristics or implementation. And so I've broken this down into several steps which address relevant questions. Okay, so do we need to define the neural network synapse connections? I mean, yes, but this is a pretty simple neural network, so we're just going to assume that's fully connected. Every single node is connected to every single node from the layer that follows it. But in this case, right, we have 4 input nodes that all connect to a single output node. So fully connected is not that complex. Step 4b is to define the learning rate coefficient. We're going to use 0.15. Step 4c is to initialize the synapse weights and biases. We're going to do this randomly using values between 0 and 1. And so the third synapse weight, or the synapse weight between nodes 3 and 4, has an initial value of 0.03. The synapse weight between nodes 2 and 4 has an initial value of 0.22. The initial synapse weight, or the synapse weight for the initial iteration between nodes 1 and 4 is 0.1, and we initialize the bias offset to 0.5. And next, we choose an initial training sample, and we're going to choose the fifth. So what we're saying is that for iteration 0, for the first iteration or the 0th iteration, we are using training sample number 5. So any place you see x superscript 0, that's the same as x superscript 5, with 1 being bracketed and 1 being in parentheses. The 0th iteration is using the 5th training sample. And then so we can see what our inputs will be. So our ideal output for the 5th sample is 1. The input, the third element of the input for this 5th training sample is 0. Second is 0. First is 1. And then this 0th state is always a negative 1. So if we go back and look at the table, we expect to see 1, 0, 0, 1. All right, so we count. So 1, 2, 3, 4, 5. All right, so we're dealing with this row right here. So we expect to see 1, 0, 0, 1. Okay, so that matches. That's good. All right, next step. Right, and this was always more practical. Develop the necessary software. We have a MATLAB script that we're using for this, and we're going to demonstrate that in a second. Step number 6, and this is probably the most interesting part, right, is to begin training the model to yield the optimal model parameters, in this case, the synapse weights. So the first step within here, so step 6a, is to evaluate the model to generate y sub est for the first iteration, and this requires us to use the 5th training sample. Okay, so we've already declared our model. We know that the estimated output for the 0th iteration is equal to taking our activation function and applying it to the weighted sum of the synapse weights and the inputs. So we sum this from k equals 0 to k equals 3. Now over here, you can see we've broken this all out. Same activation function. We have the synapse weight between nodes 3 and 4 times the input coming from node 3, and then we move on down the line. This last piece right here is effectively the bias offset, right? It's the sum of this negative 1 value times this synapse weight, and together that gives us our bias offset. Down here, all I've done is plug in the actual numerical values, right? We got all of these from the training data table, and these were the values that we initialized. Okay, and so what we end up with is an estimated value, y sub est for iteration 0. We apply the activation function to a value of negative 0.4. The unit step activation function, whenever it accepts a value less than 0, it spits out a 0, and so we end up with a 0. Okay, now we'll note that this doesn't equal the ideal value, right? The ideal value is a 1. So we know that we will have to apply an update here. So step 6b requires us to begin updating the synapse weights for this 0th iteration. Now we're going to assume that the bias offset is constant. It remains constant with a value of plus 0.5, and that works out fine for this example. Now we need to update 3 different synapse weights, right? Because we have the synapse weight between node 1 and 4, our output, node 2 and 4, our output, node 3 and 4, our output. We already explained and demonstrated what our learning rule was. Right over here, we have the synapse weight between nodes 1 and 4. We have the initial condition for that. And we add to that the product of 3 different elements. Right? We have the first input, x superscript 1, for the 0th iteration, which we know is the same as the 5th sample. We have the difference between the ideal and the estimated, which will be 1 minus 0, right? We just came up with a value of 0 for that on the previous slide. And this will be a value of 0.15. So here you can see the values plugged in. 0.15, 1 minus 0, 1, plus the initial condition gives us an updated value of 0.25. Do the same thing over here. I don't think I need to explain every element, right? Our initial synapse weight value was 0.22, and this whole piece goes away because the second input is a value of 0, so we end up with the output being equal to the input. All right, the updated value is the same as the one from the previous iteration. And then for the third synapse weight, we started off, or we had an initial guess of 0.03, and this one also stays the same because x superscript 3, or the third input, is a 0. So this is the only one that changes going from iteration 0 to iteration 1. Now that's not going to be the case for every iteration, right? Because for other training samples, let's say we take the last training sample, all 3 of these inputs will have a value of 1. Okay, now we're not done with training yet. We still need to check for convergence, but we kind of already know the answer here. We saw in several locations that the difference between the ideal and the estimated is not equal to 0 or is not close to 0. And so this is much greater than 0. I mean, 1 is greater than 0, so we don't have convergence. And then step 6D would be to increment the iteration and continue. So we don't have convergence. We got to return to step 6A. And this is a preview of what step 6A would look like, where we would recalculate this estimated value, but now for iteration 1. Using the same equation, except now we use the updated synapse weights, right? The ones that we calculated right here, here, and here, as well as a new set of inputs. Now, I didn't explicitly say which one it would be, but for the next iteration, we would have to choose, right, what training sample would be associated with that iteration. We could pick anything. And generally, we do try to randomize that. We don't want to go through the training samples in the same order every time, because that can introduce some forms of bias. And then finally, once we've run through this a bunch of times, hopefully, eventually, we do reach convergence. And at that point, we have a trained model, and we can verify and test it. And this will be done via MATLAB. So here is a graph generated by MATLAB, and it shows the training process. On the x-axis, you have the iteration. Okay. On the y-axis, you have several values. So the red line is the synapse weight between 1 and 4. The blue line is the synapse weight between 2 and 4. The green line is the synapse weight between 3 and 4. And the yellow, that's an interesting one because that shows the error. So you can see here, it makes sense that we've reached convergence around the 45th iteration or so because our error is flat at 0. We also see that we don't have any more change in our parameters. Those are also flat. So we have 2 indicators that we've reached convergence. We initialize those values. As you can see, the first one was initialized, I think, to, we can go back. What did we initialize it to? The first one was initialized to 0.1. So we start here around 0.1, we end up with a value of 0.55. The second one was initialized to 0.22, we end up with a value of 0.52. And the third one was initialized to 0.03, and we end up with a value of negative 0.12. So this demonstrates what the machine learning process looks like for this error correction algorithm when you consider the x-axis or the independent variable being the iteration number. Okay, so here's the code that we used. There's 2 QR code links over here. One is to the actual script, so you can download it, and the other one is to Octave Online. I know some of you may not have access to MATLAB, so if you don't, please check out Octave Online. You should be able to run this code for free in your browser. Okay, so let's take a look at the code itself, the script. Now in the beginning here, what we do is we initialize all of our synapse weights as well as our learning rate. Then we move on to defining the training data set. This is pretty similar to how we defined it for the previous logistic regression example. We then tell MATLAB that it hasn't converged yet, right? This Boolean variable will take on a value of 1 once it's converged. We then tell the algorithm that we're starting at iteration number 1. Perhaps I should have made that iteration 0. We then tell the algorithm that we want, for that first iteration, we wanted to use training sample number 5, right? We had to tell MATLAB that, or else we wouldn't necessarily get values that matched the math that we did here. All right. So then we go ahead and start a while loop. So what we say is that while convergence has not been reached, while this Boolean variable is equal to 0, keep going. Now here, This is a line of code that only runs for every iteration after the first, and it randomly chooses a training sample to use for that iteration. I use the if statement to eliminate it for the first iteration, again, to make sure that we keep using the fifth training sample. Then we go over here, we load our inputs as well as our ideal output. So input 1, input 2, input 3, ideal output. We then calculate our H value as the weighted sum of the synapse weights and the inputs. Okay, we then apply, here's where we apply our activation function, which yields a value of either 0 or 1. We increase the iteration number, and then here is where we apply the update expression. Here's where we update the synapse weights. So like I showed, we start with the synapse weight from the previous iteration plus the input times the error times the learning rate. Here I just quantify the change in the y value between two iterations. And then here I check for convergence. And what I say is we're not going to even check for convergence until the 25th iteration. And then I went ahead and plotted the results as shown on the previous slide. So again, you can download this code using the QR code here. You can download the script using the QR code here. And you can download or access Octave online using the other QR code. Next, I want to present the homework exercise that we're going to be assigning, and please submit your solution in the comment section. That could be the final solution, that could be code. You could copy and paste the code. You could provide a link to GitHub or to Dropbox, whatever is convenient. Okay, so I want you to consider a traditional OR gate, but in this instance, a 3-input OR gate. Okay, and obviously that's associated with Boolean logic, so this is somewhat like the homework from the previous module. And again, use Octave online if MATLAB isn't accessible. And I want you to apply the Perceptron machine learning algorithm to that data set. You can use much of the code from the example that we just presented a second ago. And I want you to yield an optimal set of synapse weights that predict when the OR gate should generate a positive or negative output. This also has a part B. I want you to try to apply the same approach to a 3-input exclusive OR gate, XOR gate, and tell me, why does the first one work and the second one does not? We've actually already presented the answer to that question in one of the previous modules. So to summarize what we've discussed here in this 5th module on artificial intelligence, we began by discussing how to characterize a machine learning implementation, right? We must define the learning approach or paradigm, the rule or strategy used, the components that we employ, as well as the application that we're looking at. This module, right, demonstrated the implementation of a supervised machine learning algorithm, which was our approach, that employs a basic error correction rule, that was our rule or strategy, in conjunction with a single layer perceptron neural network, that was the model component, for binary classification, and that was the application. Right, for the proposed example, this machine learning algorithm yielded a solution similar to that yielded by logistic regression in terms of accuracy and performance, not necessarily in terms of process. However, I think one advantage of this as compared to the logistic regression is that we better understand how the optimization process here worked. Whereas for the logistic regression, we kind of just relied on a minimization function from MATLAB. This basic machine learning example introduces the concept of iterative machine learning that I think will be really useful in many future modules. The next topic is a really cool one, a really interesting one. We are finally going to dive into using Python and PyTorch for machine learning. I think this is very important because these are more practical tools that many data scientists and engineers and computer scientists use in the field when they're working on machine learning problems.